Swayam Prabha. Digital India. Educated India.
So, I just thought we'll start the lecture today, do a small recap of what I did at the very end of the last class, because I went through that very fast. Okay, we were seeking theta as theta 1 z plus theta 2. Okay, and if you remember, theta was written as theta 1 z plus theta 2. This is what we did in the last class, and we were yet to determine one of the constants. We had 4 constants. 2 constants were put to 0 because of the boundedness condition, and we used the condition to the flux at the wall to get one constant, and one constant was remaining, which I didn't do. I told you should do it. I'll just tell you how to do it. Okay, so basically what I want to do is I want to integrate this thing on the left hand side, and you will get this is 0 to 1, 2 pi comes here, this r star cancels with this r star, this dr star goes away, and this is d of r star d theta by dr star. Okay, and this can be written as 2 pi of r star times d theta by dr star evaluated at r star equal to 0 and r star equal to 1. And this is nothing but at r star equal to 0, this is going to be 0 at the lower limit, and at the upper limit r star is 1. The dimensionless derivative was 1, d theta by dr star. So, I put those boundary conditions, this becomes 2 pi. Okay. As far as the left hand side is concerned, what I am going to do is, remember that theta is a function of r and z. I am integrating with respect to r, and this derivative is with respect to z. So, I can take the derivative outside, because these limits do not depend upon z. Okay, these limits depend only on, they are constants, they are 0 and 1. So, I can write this as d by dz of integral 0 to 1 minus r star squared times theta times 2 pi r star dr star. This is my left hand side. Okay. So, basically what I have to do is, I will write this again, I am just rewriting that again, integral 0 to 1 minus r star squared times theta of r comma z times r star dr star equals 1. The 2 pi cancels off, 2 pi is same on both sides. Okay, and I will integrate this in the z direction to give me from 0 to some z. So, integrate in the z direction from 0 to some arbitrary z. Okay, and what I will have is, and remember at z equal to 0, theta equals 0, because that is how we define theta, t minus t naught. Okay. So, at z equal to 0, t is equal to t naught, so theta will be 0. So, when I integrate this, d of this integrating the z direction, I will get integral 0 to 1 minus r star squared theta of z, theta multiplied by r star dr star equals z. Okay. So, what I have done, I have just integrated, I have taken the dz to that side, integrated, I get z, d of this integrate only thing that is changing is this is going to be a function of z. So, z at 0 to z at z, z at 0 is 0. So, lower limit is 0, upper limit is theta. Okay. I have not written one more term because that term will be evaluated at theta equal to 0. Is this clear? So, basically this is what I get. Now, what you have to do, and which I am not going to do, is substitute the expressions for theta 1 and theta 2 that we derived in the last class, okay, in terms of r, and integrate this and equate this, then you will find that unknown constant C3 or whatever that unknown constant was, okay. Using this, we find the third constant. So, let me just recap. So, this is just the energy balance equation which we wrote. We have integrated this in the r direction, okay, and all I have done is substituted for and then recognize that this is a function only of z, okay, because I am integrating in r. So, I am write this as d by, so now the partial derivative has become the total derivative, because after integrating in the r direction depends only on z, okay. I get d by d instead of this equal to this thing also integrated in the r direction, I get 2 pi, and now I am integrating again the z direction along the length of the channel. So, first integrating in r, then integrating in z, and then equating, I will get the unknown constant, okay. That is just some integration which you have to do. I think this constant is some number which I will not tell you, okay, you have to find out, okay. But anyway, this is discussed in Gary Leal, so you can look at it. One of the things we will do is we will let you know which portions of Gary Leal contain these problems that I am doing. So, you can go and refer to it, okay. Okay, so that is it. So, now I want to move on to the next problem, and the other thing which I want you to remember is that this particular solution is valid only for large distances into the pipe, okay, because we have not bothered to satisfy theta equal to 0 in the solution. In the integral balance we put theta equal to 0, but for the differential equation where you have theta 1 z plus theta 2, we did not impose that. In an integral balance I am satisfying the theta equal to 0 condition, okay. So, these are subtle points you have to understand. So, the point I am making here is the solution which you got is a approximate solution, okay, which captures the important things going on in the channel. Look at this problem of solidification at an interface, okay, and this again is a problem of heat transfer, and let me first pose the problem to you before we start doing anything else. So, I have a cylinder, okay, and this contains liquid. So, cylinder has a liquid at temperature T1. So, because it is a liquid, it has to be more than the freezing point. This temperature T1 must be more than the melting point, okay. This must be greater than Tm, the melting point. So, Tm is the melting point of the liquid or the freezing point, okay. Tm is the freezing point for water 0, for example. So, this is liquid at more than 0 degrees. Now, what I am going to do, so everywhere it is liquid, I am going to, the walls, the curved surfaces are insulated. So, what that means is there cannot be any heat transfer into the liquid from there, okay. And I am going to say height of the cylinder is infinite. This is extending to infinity here, okay. What we are going to do is we are going to suddenly lower the temperature or maintain the temperature at the bottom at let us say T0. The bottom surface is suddenly cooled and kept at T0. What is T0? Is a temperature which is lower than the freezing point. So, as soon as you keep it at T0, what is going to happen? The liquid adjacent, and this is Z equal to 0. This portion is Z equal to 0, okay. That is my bottom surface. As soon as the temperature becomes T0, the liquid is going to freeze, correct. With water, you make it minus 10, whatever it is going to freeze, you are going to get solidification. And this, you maintain the temperature here, what do you expect to happen? You expect that there is going to be more and more heat which is going to be removed from this system. No heat can come from the sides, okay. So, this liquid is going to give the heat more and more, and you are going to take away the heat from the liquid, okay. And therefore, as you take away the heat, you are going to have a front, an interface between the solid and the liquid, and what is going to happen is this interface is going to keep on increasing, you understand. So, basically you have, this is the solid and this is liquid. You will have an interface, and you wait for a long time, you have more and more solidification, okay. More and more things will get freezed and will get frozen, and this interface keeps moving up, okay. This point I am going to call it Zm. Zm basically tells you interface at time t. Now, we are going to keep our life simple in the sense that we do not want to worry about a 3-dimensional problem, okay. So, the only thing we are going to say is that first of all we are going to assume theta symmetry. So, you have only Z variation and R variation, and what we can do is, because this front is moving, we can assume that this interface can, because of the no-slip boundary condition, you will expect something like a radial profile. So, for the moment let us not worry about the radial profile, because we want to try to understand how to solve this problem analytically, okay. So, we are going to assume that there is no variation in the radial direction. Clearly there has to be a variation in the axial direction. So, basically I am looking at a problem where things are varying only in the radial. So, this is an assumption. So, when you are solving a problem, two things: you can ignore something because you are ignorant and you can make a mistake, or you can ignore something because you have made an assumption and you know that you ignored it and then proceed. So, what I am doing is I am trying to be not ignore it. I am trying to tell you that look, I am making an assumption. If I just arbitrarily solve it in the z direction, then I mean I am being ignorant about certain things. So I am not being ignorant, I am just telling you I am making an assumption here, okay. So theta or the temperature is a function of r, z, theta and t, okay, in cylindrical coordinates. Theta symmetry implies t is a function of r, z and t, and I am interested in a one dimensional problem. So which dimension am I interested in? I want to retain the dependency in the z direction, not in the r direction. So I am going to assume that the variations in the r direction are very small. So this assumption, this can be justified in the limit of if the diameter of the cylinder is very small. If the diameter of the cylinder is very small, I can assume that the temperature is going to be uniform, because any change, the conduction is going to make it equal, okay. So basically we assume temperature is independent of R. This is valid for small diameter of the cylinder. Okay. So if the diameter of the cylinder is very small, the heat has to travel a lesser distance. The resistance to heat transfer is very small. Okay, the resistance depends upon the distance over which you have to travel. So I can assume it is uniform. That's what we are doing. Okay, and of course I need to make sure that this temperature at the bottom, which is T0, is also uniform. It is independent of R, because if this guy depends on R, then the inside also will depend upon R. Okay, so basically to do that. So I am trying to tell you the temperature is therefore a function only of Z and T. Okay, that is the thing. The other important point is, when you have freezing, okay, or when you have a phase change, it is usually accompanied by a density change. For example, when water freezes to ice, the density becomes lower, because of which the ice is floating. Okay. So the density changes, and so what I am going to, so if you have liquid converting to solid, there is a change in the density, and because there is a change in the density, what is going to happen is there is going to be some volume created, and because of which there will be convection. So but in the solid, the only mechanism of heat transfer is going to be conduction. Okay, there is no movement. So as far as the solid is concerned, there is only going to be heat transfer because of conduction. In the liquid, I will have conduction and convection. Why? Because whenever there is a phase change, there can be change in the density. So 1 gram of solid may have frozen, it may give you 1 gram of liquid, but the volume of the liquid is either different from, so whatever volume is going to be generated by freezing, when it gets transferred to liquid, it will be different. Okay. So basically the point I am trying to make here is, in liquid you have to consider convection also. Okay. Whenever there is a phase, whenever there is a density change because of phase change. Okay. So in solid, the heat transfer is by conduction. Okay. And in liquid, we have conduction and convection if there is a density change with freezing. Okay. So, I am going to be a nice guy and just going to assume that the density does not change. Okay. So, we will just not worry about convection in the liquid. But even if you include convection, whatever I am doing, you can extend it and you can do the same analysis. Okay. So, I just wanted to inform you that right now I am going to assume that there is no phase change, which means there is going to be no convection induced in the liquid. Okay. Only conduction. So, I am going to have only conduction, again this is an assumption I am making. I am going to assume only conduction in the liquid and in the solid. Okay. So, that is the again an assumption I am making, but if you do not want to make the assumption, you can include the convection in the liquid and the same approach can be used. Okay. This has been done in Galileo. Okay. So, I am just keeping my life simple. For now, we assume rho s is equal to rho L and consider only conduction in liquid and solid. Okay. So, that is basically what we are going to do. For now, so this is my solid and that is my liquid. In the solid, what is my this thing? Rho s Cps dTs by dt equals Ks d square Ts by dz square. I am of course keeping all my properties are constant. Okay, I am treating all properties as constant, although they are functions of temperature. I am assuming all these are constant. So, this is the problem in the as only conduction. This is something you are used to, transient heat conduction problem. Okay. Only thing is this is valid from what is the domain to which it is valid? 0 less than z less than zm, which varies with time. So, the validity of this equation is in the interval from 0 to zm. Okay. And I am going to write this in a nice way by calling this dTs by dt is equal to alpha s d square Ts by dz squared for 0 less than z less than zm. Similarly, in the liquid, I will have dTl by dt equals alpha L d square TL by dz square. There is some thermal, and alpha is the thermal diffusivity K by rho Cp. Okay. Alpha is K by rho Cp. For liquid it is alpha subscript L, for solid it is alpha subscript S. And what is the domain over which this second equation is valid? It is Zm less than Z less than infinity, because it is going up to infinity. Okay. So, I have written the boundary conditions which we have to solve. Of course, you understand that I need to keep both. So, this is very similar to the problem which you people are used to. In undergrad, you are looking at composite slabs, right, 2 slabs, and you will have some copper and something else, and you have a temperature gradient, and you have a linear profile here, and you put boundary conditions and you solve, and you get linear profiles. So, something similar, there are 2 different materials, one is solid, one is liquid. Okay. But one small change, that is it is extending to infinity, that is one thing. Second thing, the boundary is moving, that is the other complication. Third thing, there is a phase change. Okay. So, these are the differences from what you have already seen. Okay. And what you have already seen, you got a linear profile, remember. So, So, similar to the composite slab, but here temperature is a function of Z and T, Zm is a function of T, okay, the extent to which the composite slab, the interface is solid, does not move, and there is phase change at the interface. Okay. So, what are the boundary conditions I need to impose for solving this? At Z equal to 0, I have temperature is equal to T naught. At Z equal to infinity, I have temperature equal to what do we have? T1, because initially this liquid is at temperature T1, by the time this heat transfer takes place, it starts affecting at infinity, it will still remain T1. Far away is going to be T1, whatever the initial temperature of the liquid was, okay. Here I made it suddenly T0, it remains at T0. Now, what is going to be the temperature at the interface? At the interface is where we have the phase change, okay. So, at the interface, this is going to be less than Tm, here is where it starts freezing. So, the temperature is going to be equal to Tm here, okay. So, temperature at Z equals Zm, temperature equals TL equals Ts equals Tm. The solid temperature and the liquid temperature both are equal to the melting point temperature. So, you may think that I have a second order equation, I have two, for each domain I have the boundary condition is, I know here, I know the boundary conditions, my problem is solved, okay. I mean you can use the usual method, but what is the complication here? The complication here is the domain extent Zm is not known to me, I have to find out Zm. That is my objective of interest. What is the interface position? What is my freezing front? My front is freezing and moving, I want to know how does it change with time, okay. So, I need one more condition, but we want to find the rate at which Zm changes. What I am saying is Zm is unknown. If Zm is known, Zm is what? The position of the interface. If Zm is known, the problem is solved, but Zm is changing and that is determined by the problem. It is not something I am fixing. I want to find out what Zm of t is. I want to find out how the interface changes with time. There is an unknown, there is a dependent variable, okay. And what that means is I need to have one more condition, one more equation, which will help me find out this Zm, okay. I mean if the Zm is fixed, then I do not need to do anything. These equations and these boundary conditions I can use, put some initial condition, and then because temperature is T1 here, temperature is T1 everywhere, and solve. But because Zm is not known, I need one more condition, and what is that condition going to come from? It is going to come from the fluxes, because whatever I have to do a flux balance at the interface, okay. So, this Zm, this is coming from flux balance at the interface, okay. So, now let us understand what is going to happen, and remember when there is freezing or any phase change, there is some latent heat which is going to be released or absorbed, okay. So, basically what that means is, normally what you do is at the interface we normally put fluxes are continuous. That means this is at z equal to Zm, because the interface itself doesn't have any mass, it is an idealization, right. So, whatever heat is coming from the liquid is going to get transferred to the solid, or whatever heat is coming from the solid is going to get transferred to the liquid. So, what we will do is we will put something like minus K S dTs by dz equals minus KL dTl by dz. This is the equality of fluxes. Okay. This is fluxes are equal. I can use this if there is no latent heat effects. And this is what you have done when you talked about the composite slab problem. You will say the temperatures are equal and you will say the fluxes are equal. In the composite slab problem, the temperature is also unknown. Temperature is unknown, fluxes are unknown. Okay. Here the temperature is fixed, it is melting point. So, it will look like I do not need something extra, but I need something extra because the fluxes are, the interface position is not known. So, how do I get this interface position? So, supposing this interface is moving at, if interface is moving at dZm by dt, that is the velocity, Zm is time, dZm by dt is the thing, then what is the amount of heat released? What is the volume dz by dt, not amount, rate of heat released due to the latent heat. So, if the area is A, is going to be A times dz rho multiplied by rho s whatever times Lm times area times dZm by dt. I am saying that the latent heat is I am defining on a per unit mass of solid. Okay. So, the basically Lm is the latent heat, okay, it is not length, it is latent heat. Rho times A times dz is a volume multiplied by rho is a mass. So, that mass is per unit time is being converted, is being frozen. Okay. So, because it is being frozen, that is the amount of heat that is going to be released. And so, this heat that is being released has to be balanced by the fluxes. So, that is one difference from your classical problem that you have encountered before. Okay. So, basically because you did not have phase change before. Look at the situation, temperature is high here, temperature is low here, and temperature is even more low here. Okay. So, heat is actually coming from the top to the bottom. If I want to look at it physically. So, the flux in the negative z direction is K dt dz. This is the flux in at z equal to Zm. This is the heat rate multiplied by area. Okay. Because I put an area there, I put a multiplied by area, become interested in total amount of heat transfer rate at which heat is coming. Okay. So, this is rate of heat transfer from liquid to the interface. why is it? Because I do not have a negative sign, that means this is flux in the negative z direction. Therefore, it is, if I have a negative sign, it is the flux in the z direction. There is no negative sign, so there is a flux in the negative z direction. The negative z direction is from the liquid to the interface, okay? Because the positive z direction is upward, z equal to 0 is at the bottom. So, similarly, A times Ks times dTs by dz at z equal to Zm equals rate of heat transfer from interface to the solid, okay, and there is heat being liberated, which also has to be removed. So, that this is the heat coming in, heat is being taken out because of the conduction of solid, and then there is being heat generated because of this thing. So, this is like therefore, the boundary condition I have is KL A times KL times dTl by dz at z equal to Zm equals Ks times A times dTs by dz z equal to Zm plus that thing here rho s L Lm is latent heat times A times dZm by dt, okay. So, A cancels off everywhere, and that is my flux equation, fluxes, the fluxes are balanced. So, whatever is the heat that is coming in plus whatever is being generated is being carried out by the solid, okay. So, that is what I am writing. So, this is another important modification, and this is the equation which tells you how the Zm changes with time. So, now I think I am all set to solve this problem, because I have written down the boundary conditions and everything. So, you understand why we need this, and what I will do is I am going to define theta, my dimensionless variable, as okay. And what is the advantage of this? Because then at z equal to 0, theta at z equal to 0 is 0, theta at z equal to infinity is 1. Okay. Because I have boundary conditions T naught here, T1 there. So, in terms of theta, I can write my differential equation now as d theta s by dt. I have not made the equations dimensionless, okay. I am keeping these guys as it is, only temperature I have made dimensionless, and theta s of 0 is 0, and d theta s by dt, d theta l by dt is alpha l d square theta l by dz squared, and theta l of infinity is 1, okay. So, just to give you an idea, I mean this dimension is going to infinity, okay, and I am going to use what we saw earlier, similarity transform, to find a solution, which is why I have not bothered to make the space and time dimensionless. Otherwise, I would have made the space and time dimensionless. So, our approach is again something similar to what we have seen earlier. We use similarity transform in the case of that velocity problem. Plate is moving, there is an infinite extent of liquid, and there was no length scale, and then we said we will use similarity transform. Here again, no radial variation, in some sense there is no length scale, okay. So, we are again using similarity transform. And if you remember, it was very similar to what we did earlier. You had dou u by dou t equal to nu kinematic viscosity times d square u by dt squared. by dy square. Only thing is same thing, but I have two equations, two phases. So, I have to apply similarity transform 2 times kind of thing, okay, and then seek the solution. So, there will be one similarity variable here, another similarity variable here, and then I put the boundary conditions. So, let me, so I think the moral of the story is that first you have to learn how to formulate the problem, okay, and that is what I have been trying to tell you. My problem is how to formulate. Once you know how to formulate, once you know how to make the assumptions, or once you have made the assumptions and write down the equations, then you worry about solving, okay, and you need to know what the assumptions are. So, that is the reason I spent so much time trying to explain to you what these assumptions are. Then you will get a solution, see if that solution makes any sense. If that solution does not make any sense, either you made a problem in solving the problem, or your assumptions were ridiculous, which is why you are getting physically non-intuitive results. So, you have to go back and relook at the assumptions, and then again you have to formulate the problem, again solve. So, that is how you have to do it. So, I mean what I have done is just trying to tell you that any problem, I am just illustrating that with this example. So, tomorrow you have some other problem you are working on for your project, for your research, you need to sit down and see how exactly you are going to formulate what is the physical problem, then write the corresponding equations, write the make the assumptions, then you sit down and start worrying about solving, okay. So, I am going to I think I am pretty much done with this. I will tell you to do only one thing and then define, okay, we use similarity transform to solve this, okay. Define eta s as z divided by 2 times square root of alpha s t, and eta L as z times 2 times square root of alpha L t, okay. Is exactly earlier we had used eta as z divided by square root of nu t, okay, when we solve that Rayleigh problem. What have I done? I have just like out one extra 2, I put an extra 2 there. I want you to do exactly what we did, convert this partial differential equation to eta, okay, because I do not want to do it tomorrow, I mean the next class, but I want you to follow the same steps as what we did in this earlier problem, but with this extra 2, and tell me what is the differential equation in terms of eta, okay, that you will do, because you just have to do whatever I did earlier, and then once you tell me what the equation is with respect to eta, then I will tell you how to solve, okay. Thank you.